Hi everyone, and welcome back to the Chapter 4 lecture videos. In this video, we'll talk about how bloodstain patterns form. Bloodstains are impacted in a fairly consistent manner by the context in which they're formed. The releasing and receiving surface, as well as the distance between the two surfaces and the angle of release, are all going to impact the bloodstain shape. The shape of a releasing surface, specifically whether it has a sharp or pointed edges, or whether it's smoother in nature, is going to impact how big the bloodstains are. Because a blood drop's surface tension is so high, smoother surfaces will hold blood onto them longer, and that's going to result in larger drops. Drops from small pointed surfaces may be smaller in area because less blood is going to accumulate before dropping off the surface. The characteristics of the receiving surface also change the bloodstain. Bloodstain shape is affected by both the texture and the porousness of the surface that the blood is deposited onto. Smoother surfaces are less likely to break the surface tension of the blood drops, so the blood drop will remain spherical in nature as it drops onto the surface and results in a single circular stain. Rougher surfaces are more likely to break the surface tension of the blood drop, and so they're going to cause those irregular shapes like the one you see here. Now, I do want to pause here for a second and talk about some of the vocabulary as it applies to this specific spatter that you see from the surface drop. You can see that the impact has broken the blood droplet into multiple stains. The main drop in the center is called the parent drop, and that's where all the surrounding blood stains originate from. The bloody lines coming out from the parent drop are called spines. These are pointed edges of the stain that can help determine the direction that the blood traveled. Sometimes the surface or the force is enough to break the bloodstain into multiple pieces, and that results in tiny satellite spatter like shown in this image. Okay, now back to our discussion about what causes changes in bloodstain formation. Whether or not the receiving surface is porous is going to also affect how the blood is absorbed and the shape of the resulting bloodstain. On the left, blood is deposited onto non-porous crime scene tape, whereas on the right, blood's been dropped onto a porous coffee filter. You can see that the bloodstains deposited onto the non-porous surface remain very circular in shape. On the other hand, the blood dropped onto the porous coffee filter has been absorbed into the material, and that causes the blood drops to lose their coherence and become misshapen. Bloodstain deposits onto porous surfaces will also dry faster than droplets of the same size that are deposited onto a non-porous surface. The distance between the releasing and the receiving surface matters too. As blood falls, it's going to gather speed due to the force of gravity, and that speed will affect how much spatter is created. The more distance between both surfaces, the more likely the impact will overcome the surface tension of blood, and spatter will be created on the resulting bloodstain. Finally, the angle of force will also create distinct shapes in the bloodstain. If the blood drop is dropped onto a surface at a 90-degree angle, so it's perpendicular, the bloodstain will be circular because the force will spread the stain evenly in all directions. If, however, the bloodstain hits the surface at an angle, then the resulting bloodstain will be elliptical. The smaller the angle between the force and the surface, the longer and thinner the bloodstain will be. For example, here on this slide is an image of a bloodstain that was dropped onto a surface from a 90-degree angle, and you can see that the bloodstain is almost perfectly circular. When the blood droplet hits the surface at an angle, the force of the blood droplet's movement causes it to continue to move on the surface in the same direction that it was moving before it hit. This creates a tail at the end of the blood drop that points in the same direction as the force applied to the blood droplet. So think of it like skipping a rock on a lake. If you throw the rock into a lake using an underhanded toss, right, you just whoop, it falls into the lake at approximately 90 degrees and just plops down into the water. If, however, you throw the rock onto the lake at an angle and you skim it, it's going to skip across the surface, creating a trail down the water, and that trail is in the direction of the force. So you can kind of think about that in terms of bloodstain. As you can see from this image, even a small difference in the angle between the blood drop and the surface can create a large shape distortion in the final shape of the bloodstain. As the angle increases, the bloodstains get more and more elongated. The long, thin, very elongated bloodstain found at the bottom tells investigators immediately that the blood was projected onto the surface from a very small angle. These shape differences can therefore be used to help investigators determine where the bloodstain came from in terms of the three-dimensional scene. To help investigators reconstruct the events that caused the bloodstain, they're going to use the directionality and the angle of the blood impact to determine the approximate location from which the blood originated. The simplest way of doing this is by stringing, and that involves using physical strings attached to the bloodstain. Investigators can use the directionality of the bloodstain only to determine the area of convergence. And this is a 2D measurement, meaning that it can only give us the location of impact in terms of the height and the width of the wall. You can see this area of convergence depicted here with the location where all the strings overlap, the most likely area of original impact. The stringing technique you see in movies and television usually focuses on the area of origin, and that's the 3D dimension location of impact. This provides us not only the height and the width of the impact location, but also how far away from the wall that the impact occurred, directionality of the stain when they're attempting to locate the area of origin. However, to identify the 3D location of the impact, investigators also calculate the angle of impact, and they do this by using geometric formulas that utilize the bloodstain width and length to calculate the incoming angle. Although historically physical strings were used in this analysis, advances in laser and imaging technology have seen an increase in technological procedures designed to calculate and document area of convergence and area of origin more easily. For example, this image is from a software program called Hemospat, which is specifically designed to calculate area of origin from bloodstained photographs uploaded into the software. The concept of stringing still applies to the calculations, but programs like this incorporate a 3D mapping component, so investigators can create 3D sketches of the crime scene with the strings visualized while not actually requiring physical strings to be used within the scene itself. All right, well, that wraps up part 2 of the lecture video. Join me in the last lecture video for this chapter as we discuss the common bloodstain patterns that crime scene investigators come across.